In this video, we're going to look at what's called the addition rule for probability. We're going to start by considering an example, and this example it's to do with a deck of cards, and we're talking about event A is drawing a red card, and event B is drawing an ace, 2, 3, 4, or 5. And we're going to consider this by looking at a Venn diagram. So, we're going to draw our sample space, and inside we'll draw A, and that is getting a red card, and we'll draw B, that is getting an ace, 2, 3, 4, or 5. Now, to fill in this Venn diagram, we need to think about what we have. Well, we know there are 26 red cards in total, so that's 26 over 52, the probability of A, and the probability of B is, there's 1, 2, 3, 4, 5 of them, and there's 4 suits, so that's 20 and 52. But what about in the middle? In the middle, that is, it's both red and an ace, 2, 3, 4, 5. Well, there's the ace, 2, 3, 4, 5 of diamonds, and the ace, 2, 3, 4, or 5 of hearts. So there's 10 of them. So in the middle there's 10. And remember, this is the probability of A intersected with B is equal to 10. So that means we can fill in the other bits. The probability of it just being red and not the other one is now 16. So the total inside the red circle is 26. And just being B is 10. So the total inside the green circle is 20. Finally, we need to add the extra bits. That doesn't fulfill any of them. In this case, that's 16 to make the total up to 52. Now, what the addition rule considers, the addition rule is when we're talking about or. What's the probability of it being A or B? And mathematically, we talk about that is the union. So, mathematically, we're talking about having the union here, and the union is the probability of A union B, and that is the probability of A or B, or indeed both of them. That's what we mean when we say or. So when we say A or B, we actually mean A, B, or both of them. It doesn't mean it has to be A or B, but not both. We always mean both in this case, unless it specifically says that it is only one of them. So in this case, A or B or both, this is equal to, well, that's the 16 plus the 10 plus the 10. Out of 52, when we add that up, we get 36 out of 52, which simplifies to 9 out of 13. So to find A or B or both, we added together the 3 numbers, the red number, the blue number, the green number, just the A's, just the B's, and the intersection. Now let's have a look at how we can generalize this. So now we have 2 events, A and B. I'm going to say let the probability of A be A, and the probability of B happening be B. So once again, let's consider our Venn diagram. And we can have A is A. So we have A. And we have B is B. B. But before we can put either A or B in, remember we need to find what goes in the middle first. And in this case, we don't know what the middle is. The probability of A intersect B. Well, let's call it something, let's call it I for intersection. So that means in here, we have I. That means just A is A minus I. because the total of the red circle must be A. So if we've already got I, we have to take I off. Similarly, in B, we have B minus I, because the total of the green circle has to be B. But now if we think about what we were looking at before, which is the probability of A union B, A or B, well, that's adding up the red, the blue, and the green. So that's A, not plus, A minus I plus I plus B minus I. But that simplifies. We have an A, we have a B, and we have plus I but minus 2I gives us minus I. But now we can write this in terms of our original probabilities. Well, A was just defined as the probability of A. B was defined as the probability of B. And I was defined as the probability of A intersect B. So we have the probability of A union B is equal to this. And this is what's called the addition rule for probability. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of them both happening. And the reason we have to take away that one of them happening twice is because actually them both happening is included in A and B. So it's included twice, so we have to get rid of it. We can rearrange this formula and get a slightly different version, which is the probability of A intersect B is equal to the probability of A plus the probability of B minus the probability of A union B, just by rearranging those two. Sometimes that one might be more useful. So let's have a look at an example of how we can use this. Here we're given the probability of A is 0.6, the probability of B is 0.7, and the probability of A or B is 0.9. The first thing we'll have to find is A intersect B. Well, the first thing we notice here is that the probability of A or B is also the probability of A union B, is the proper way of writing that. So using our rule, probability of A intersect B, this is the second one we had, was the probability of A plus the probability of B minus the probability of A union B, which in this case is 0.6 plus 0.7 minus 0.9, and that is equal to 0.4. So it tells us the intersection is equal to 0.4. Now with that, the intersection, we can think about drawing our Venn diagram. We have A, we have B, we now know the intersection is 0.4. We know A is 0.6, so this means this bit is 0.2. And we know B is 0.7, which means this bit is 0.3. That also tells us that outside we have 0.1, and we can get that from A union B. We know the total of A and B, A or B, sorry, is 0.9, so there's 0.1 outside. So part B, the probability of A complement, so the probability is not in A, well, we can see that easily from the Venn diagram, that everything is not inside the red circle. So the probability of A complement is equal to 1 minus the probability of A, which is 1 minus 0.6, which is 0.4, and we can see that that's the 0.3 and the 0.1 summed together. The probability of A complement intersection B, so that everything that's not in A but is in B, and that we can see is just the stuff that's just in B. From the Venn diagram, that's easy to see. 0.3. It's the stuff that's not in A, but is in B. So not inside the red circle, but is inside the green circle. And the last part here, A complement union B, we're going to use our rule again. This is the same as the probability of A complement plus the probability of B minus the probability of A complement intersected with B. So we know all these now. Probability of A complement, well, we worked that out in part B, was 0.4. Plus the probability of B, we're given that, is 0.7. Minus the probability of A complement intersect B, we just worked that out in part C, is 0.3, which means the answer to this is 0.8. And again, we can see this from the Venn diagram. It's the union of everything that's not in A together with everything that is in B. So that's the 0.4, the 0.3, and the 0.1. They're all in one of the two steps that we want, so they all add together to give the 0.8. Now there's one very special case of the addition rule, and this is when we're considering mutually exclusive events. Now remember that mutually exclusive events mean they cannot happen at the same time. In terms of strict probability notation, if they cannot happen at the same time, that means the probability of A intersecting with B is equal to 0. So a more formal way of writing this is A and B, events A and B are mutually exclusive, okay, and that is if and only if, so double-headed arrow, if and only if the probability of A intersected with B is equal to 0. That means if they're mutually exclusive, their intersection will be 0, but also if the intersection is 0, they are mutually exclusive. This works both ways. But that means we can also substitute the probability of A intersection B equals 0 into our previous addition formula. And that means that we also have the probability of A union B is equal to the probability of A plus the probability of B minus the probability of intersection, but in this case it's 0, so we don't have it. So if they are mutually exclusive, the probability of one or the other is just the sum of the two events, the probability of each of the events independently. And as a Venn diagram, mutually exclusive events look like this. A and B, they do have no intersection at all, so the two circles that represent the sets are completely separated. So that's the addition rule for probabilities for two events. If we have, they're not mutually exclusive, we have one rule, a probability of A union B is the probability of A plus the probability of B minus the intersection. But if they are mutually exclusive, we have this one here, where the probability of A union B is just the probability of A plus the probability of B.